Hello students, welcome back to the another session of the econometric methods course. In this module, we are going to see the different tests available to detect the multicollinearity problem and the possible remedies for solving the multicollinearity problem. So, we are going to see them one by one. Let us see that. There are many tests available to test the presence of multicollinearity. We will start with the simplest ones, and we will continue with the various multicollinearity tests. The first one is the most simplest. For the regression model, once the regression model is run, we can audit the R square and the T ratios. If the R square is high, but very few significant T ratios, we can readily identify the problem that the regression has got the multicollinearity problem. Just take the two examples. The first one is taken from the student Munt's econometrics book. In this, we have taken this is the consumption function. Consumption is a function of the disposable income and the liquid assets measured in terms of savings, and this is income, monthly or annual income. This is the consumption consumption regression on the disposable income and the liquid asset. This regression actually you have got to know R square, very high R bar square. R bar square is almost near 1, 0.835, but at the same time the T values given in the square bracket is very less, 0.496 and 0.453. So, in this regression R square is surprisingly high, at the same time surprisingly T values are very low. So, this is the situation where you can suspect that there exists a multicollinearity problem. Here naturally the income and the saving of the individual may be closely related, and that causes the multicollinearity problem. That is the source of the multicollinearity problem. Anyway, actually, so this problem leads to multicollinearity, and that is reflected in this very high R square and very few significant T ratios. Actually, in fact, both of them are insignificant. Second example, actually this is another regression equation in which the R square is 0.965 and R bar square is 0.9531, but both the T values of x2 and x3 variables are very low, very low. Actually, they both are insignificant, and this is the cause. Actually, this is the indication that there exists a multicollinearity problem in this regression model. Another test for the multicollinearity is pairwise zero order correlation coefficient. In the MLRM, let us take this MLRM, y is equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ui. We may first run a pairwise correlation among the independent variables. Here there are three independent variables, x1, x2 and x3, and we are running the pairwise zero order correlation, simple pairwise correlation we are running, and we are tabulating that. Actually, this is the table, shows the simple zero order correlation coefficient matrix. This one, the decision is taken based on the modulus or the absolute value of the correlation is more than 8, then we may consider the multicollinearity problem is very severe in this case. So, it may indicate the presence of multicollinearity, but it may not help identify the source, because the zero order correlation coefficient is very enigmatic one. Actually, we won't be able to identify the source of the multicollinearity problem, which variable causes the multicollinearity cannot be found because of the interrelationship between the variables. So, what I am trying to say is this simple pairwise zero order correlation matrix will help to just to say whether there is a multicollinearity problem or not. We can examine the partial correlation coefficients. Partial correlation coefficients can also be found for each of the independent variables. If the partial coefficients are higher or less than the partial the multiple correlation coefficient are 1.23 square, then we may suspect there exists a interrelationship between the left out variables x 2 and x 3. This multiple correlation coefficient is found by the auxiliary regression of x 1 on x 2 and x 3. So, the partial correlation coefficients will be found, the square of it is found, and then we will compare the square of the partial correlation coefficients with the multiple multiple correlation coefficient to identify the interrelationship between the independent variables. This will indicate the multicollinearity problem. And another method is there, that is auxiliary regression method, regression test. In this, all the auxiliary regressions are used to find the presence of multicollinearity problem and the source of multicollinearity problem. This the auxiliary regression test in fact helps both to identify the problem and identify the source of the problem. Let us take the main regression as the y1i yi hat is equal to beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i, and this is the main regression. With the data we can run this regression and we can get the this r square. This is the r square of the main regression. Then we can by in this method we will find the auxiliary regression equations. You will have as many auxiliary regressions as the number of independent variables. Here in this case we have got 3 independent variables, and so we can possibly form 3 auxiliary regressions. So, let us see now one by one. x1 is regressed on x2 and x3, that is the first equation. x2 is regressed on x1 and x3. x3 is regressed on x1 and x2. So, that is the third equation. So, first equation we are finding, we are running the regression, then we can find the r1 square, that is the this is the r square of this regression. So, we can find the r2 square and r3 square. So, if the individual auxiliary regression r squares are greater than the overall r square, then we can say there is a multicollinearity problem, there is a severe multicollinearity problem. So, this indicates the multicollinearity problem, and this is called thumb's rule, Klein's thumb's rule, and this is one way of identifying the multicollinearity problem using the auxiliary regressions. There is another way, actually this is in other words called the Farag-Glauber test. From each of the r square values we can find the f ratios, This is a statistical test, and so this will give you a very precise answer to the problem, and this is f values for each of the auxiliary regressions are found. Here k is the number of parameters to be estimated in the auxiliary equations For example, in the first equation we have got first auxiliary equation we have got 3 parameters to be estimated, and so k would be 3 here. If f is significant, then we will say there exists a multicollinearity problem, and if xi is found if I is significant, then we will say the ith independent variable is the main cause of the multicollinearity problem. That is how we can conclude the source of the multicollinearity problem. Which variable causes the multicollinearity could be identified using this significance test. Now, we will see some tests based on the variance inflation factor and tolerance index. Both are closely related. One is the inverse of the other, multiplicative inverse. Tolerance index is the 1 by VIF or 1 minus RI square. If the VIFI is greater than 10, then we may infer that the multicollinearity is high. The multicollinearity is high and is also due to the xi variable. Similarly, if the tolerance index is closer to 0, then we may confirm the presence of multicollinearity, and we may also conclude that it is due to the ith independent variable. So, this fact actually this is the test that is used to confirm the multicollinearity problem and identify the source of the multicollinearity problem. Let us see another method based on the eigenvalues and conditional indices. This method is based on the matrix x dash x. This is the data matrix of the independent variables, and from this independent data variables matrix, we can find the variance covariance matrix of independent variables. That is denoted as the variation measure sigma xi x1 square, variation in x1, and this is the covariance between x1 and x2, and this is the covariance between x1 and x3, and this is the covariation between x2 and x1, and this is the variation measure, and this is the covariation measure between x2 and 3. This is the covariation between x3 and 1. This is the covariation between x3 and 2, and this is the variation of x3. So, this variance covariance matrix is computed. From this the eigenvalues are computed. The eigenvalues are found. Let them be lambda 1, lambda 2 and lambda 3, because this is a 3 by 3 matrix, and so you will have 3 eigenvalues at the most. The k is defined as the ratio between the maximum of these eigenvalues lambda 1, lambda 2, lambda 3 divided by the minimum of those eigenvalues. So, it is a ratio between the maximum and minimum of the eigenvalues. From this we can define the conditional index, that is the square root of k. Based on this conditional index, we will try to conclude whether the multicollinearity problem is present or not. If the k is between 100 and 1000, we will say the multicollinearity problem is moderate, and similarly subsequently, if the Ci, the conditional index, is between 10 and 30, we will say the multicollinearity problem is moderate, and if the k is more than 1000 or the conditional index is more than 30, we will say there is a high multicollinearity problem or severe multicollinearity problem. So, this really helps to identify the multicollinearity problem in the regression model. So, with this we can conclude the different tests available to identify the multicollinearity problem. Now, we will see how the multicollinearity problem could be remedied once it is identified. The remedies for the multicollinearity problem. The remedy depends on the seriousness of the multicollinearity problem. In fact, the degree of multicollinearity is an important issue to be discussed. That really helps to take the problem to the solution level. Purpose of analysis, if it is for the purpose of forecasting, the multicollinearity need not be taken very seriously. The conceptual significance of the variables are also very important. If the variables are the variables that are causing the multicollinearity is very dear to the theory or the structure of the regression model, we have to take it seriously. Otherwise, we need not have to take the multicollinearity problem very seriously. And also the availability of data, right? This also really is important to solve the problem of multicollinearity. Now, let us see the remedy one by one. If MC, the multicollinearity is not serious, ignore or do nothing about the problem, because every regression model has got the multicollinearity problem. This is a all prevailing problem. This problem does crops up in every regression model, right? We will address this issue only if it is very serious. Otherwise, we can just ignore the problem. If MC is among unimportant variables, we may think of dropping the variable that causes the multicollinearity, or more troublesome variables, right? If it is unimportant and if it is very troublesome, we may consider the dropping of that variable without causing the specification error. Multicollinearity is addressed through the transformation of variables. If the model is time series model, then we may consider the first difference transformation for the regression model. Instead of running the regression model at the levels, we may run the regression model at the first difference. That is, instead of running a regression yt on x1 and x1 and x2, we may run the regression difference regression delta yt on delta x1t and delta x2t. Then if it is a cross sectional model, we may consider running the regression model with the nominal values or per capita basis. So, these transformations can be used to address the problem of multicollinearity. And sometimes the linear combination of multicollinear variables may also be explored. If there is a chance and if it is theoretically tenable, we may think of finding the linear combination of the variables instead of having the variables separately, and we may combine the variables and make it into a one, and so the multicollinearity problem can be solved. So, these transformations can really help to solve the problem of multicollinearity and address the problem. And fourth solution could be, we may add data, we may add new data, because the multicollinearity is essentially the sample sensitive issue. It is a sample issue. So, if you add the further data, the problem of multicollinearity, the severity of multicollinearity will be greatly reduced. So, adding new data is another remedy for the multicollinearity problem. And we may address the problem of multicollinearity in the polynomial regressions. So, that is also polynomial regressions are quite often used, especially when you are running the cost functions. We will run the quadratic and cubic cost functions. In such cases, the multicollinearity problem can be addressed using the running the regression in the deviation from instead of at the levels. Instead of running the output at the level, the cost as a function of output at levels, we may run the regression of the cost and on the output in the deviation form. So, that will really reduce the multicollinearity problem. There are other methods available that is also now possible. One is factor analysis. The factor analysis method can also be used. In this, we are reducing the number of variables that are regressed. The variables are grouped and orthogonal variates are found. Instead of if you have 15 odd variables, or those 15 odd variables can be grouped into a smaller number, maybe 2 or 3. The composite variables can be, composite scales can be found, and those composite scales will be not collinear in its nature, because they are orthogonal. And so, such composite variables which are orthogonal in nature could be used to solve the problem of multicollinearity. Apart from that, ridge regressions can also be used to solve the problem of multicollinearity. So, these are all the methods that are used in practice to address the problem of multicollinearity, and this will remedy the problem, will remedy the multicollinearity problem in any regression. Now, let us conclude what we have done in this module. We started off with the various tests available to identify or detect the multicollinearity problem. Then we saw the remedies for the multicollinearity problem. With this, we conclude the discussions on the problems in the regression models. We studied so far the problem of autocorrelation, the problem of heteroscedasticity, and the problem of multicollinearity. In the preceding lectures, the modules, we will be discussing about certain special issues in the regression models. So, we hope to join you in the next modules with those topics. Thank you. Thank you so much for joining this course and attending this class.